Hey there, welcome back to the channel. Thanks for being here. Well, Tesla just had their Battery Day announcement that we've all been waiting for, so here's a brief overview. Alright, here we go. I wanted to apologize beforehand because of the audio and video quality. It didn't turn out as well as it did in my testing, but I think it's still viewable and understandable, so let's jump into it. What follows is clips that are highlights from the event. I'll jump in occasionally to add something in.
So let's get started. We have a plan to halve the cost per kilowatt hour. Yeah.
Wow. Half?
And it's not, so first, before we get too far into it, let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over a meter long in a typical 2170 cell. How much we can reduce the cost and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters.
Like basically the distance that electron has to travel, and it's just much less. You actually have a shorter path length in a large tablet cell than you have in the smaller cell with paths. So this is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with.
Alright, so what they've done here is they've changed the size and shape of the battery, and in doing so, they've changed the dynamics of the battery. The industry standard used to be 18650 cells. That's what's in a lot of tool batteries, a lot of laptop batteries, all kinds of stuff. And so those were 18 millimeters in diameter by 65 millimeters in length, and for some reason they added another zero. Well, the newer ones were 2170. Well, now Tesla has come out with these other ones that are 46 millimeters in diameter, and he's saying that they're getting a much better power to weight ratio. So the batteries are lighter and they hold more power. So this is great.
Yeah, just to elaborate on that a bit, it's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yeah.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and really slows down the rate of production. And then sometimes you get the tabs wrong, and you also lose a little bit of active area. It's really a huge pain in the ass to have tabs.
Okay, so next up they describe this huge long process that is the traditional way of making these batteries, and it takes a lot of steps, and they add moisture and then they take away the moisture, and it's just this whole convoluted process, and they've really simplified it. And the next thing that they stress in here is that this whole thing is not just some pie in the sky idea that might come to fruition years down the road. This is something that they are literally ramping up right now. So that's pretty cool that it's actually here. It's not just some far off idea. Alright, next up they talk about how inefficient current factories are, and they aim to be 10 times as efficient as current factories.
86% reduction in formation investment, 75% reduction in footprint.
And then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we can. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we can do it by 2030.
Everywhere it stands.
Yeah.
That is silicon dioxide. And it happens to store 9 times more lithium than graphite, which is a typical anode material in lithium-ion batteries today.
Huh.
So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically all of that expansion stress on the particle starts cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand. You just go to the raw metallurgical silicon itself. Don't engineer the base metal. Start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
If you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
The anode would cost, with this silicon, and the anode costs $1.20 a kilowatt hour.
Yeah.
And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
Okay, so up next they talk about how important nickel is to their new batteries and how they are addressing that.
In order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel, very important. And so I think they are going to make more nickel.
Here I got up because I thought I had smelled smoke, but must have been just neighbor had a bonfire going.
At all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process costs, and zero wastewater. Much more scalable solution.
Yeah.
Wow. That's huge.
This process enables both simpler mining and simpler recycling.
Alright, this is particularly important to me because when I was taking classes for my earth science degree, classes like conservation of natural resources, we talked about how even though climate change is important and it gets a lot of attention, well, water is a huge issue because, for instance, we have an aquifer that spans a large portion of the continental U.S. and that is being depleted faster than the earth can replenish it. And we need water. Obviously, we need it for drinking and all kinds of stuff. So really what we need to do is come up with processes like Tesla has come up with here, where they're just recycling the water and they don't have any waste. So that's really cool. As a side note, Henry Ford was doing this like a century ago at the Rouge plant. So if you ever come to Detroit and you want to tour the Rouge plant, you'll learn all about that.
But it is important to say, like, okay, what is the smartest way to take the ore and extract the lithium and do so in an environmentally friendly way? And we actually discovered again, looking at a sort of first principles physics standpoint, in sort of just the way it's always been done, is we found that we can actually use table salt, sodium chloride, to basically extract the lithium from the ore. So we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
10,000 acres. And then the nature of the mining is actually, I think, also very environmentally sensitive, in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was. So it will look pretty much the same as before, and it will not look like terrible, and yeah, it'll be nice. Nice. So
Simply mix clay with salt, put it in water, salt comes out with the lithium, done.
yeah, it's pretty crazy.
Yeah. So we're really excited about this, and there really is enough lithium in Nevada alone to electrify the entire U.S. fleet.
It's one of the most common elements on the planet. Long-term, new batteries will come from old batteries once the fleet reaches steady state.
Alright, next up what they talk about is what they are calling a structural battery. And what it is they're using the stiffness of the battery cells themselves as some structure for the car. And so he gives the example of how in the early days of aircraft, they would just bolt a fuel tank inside of the plane somewhere. Well, now instead of having that extra stuff taking up the room and just having empty wings, well, what they do is they actually have wings that are filled with fuel. So the wings are the fuel tanks. So it doesn't take up extra space inside the aircraft. So I thought that was pretty cool.
So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. I mean, I really think that long-term, in any cars that do not take this architecture will not be competitive.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Wow. The batteries are going to be less than half as expensive as they are right now. Alright, so if you ask me, this is a big deal because right now, the cost of an electric car, big portion of it is the battery. The big portion of these awesome things that are coming out from like Ego and other companies like snow blowers and lawnmowers and tools that are coming out from different companies, a lot of the price is the batteries. So when you bring down the cost of batteries, it's going to make all this stuff way more affordable. And this stuff is probably going to translate to other stuff too, like cell phones and laptops and just all kinds of stuff. I think this is awesome.
All right, so stacking it up, we're not just talking about cost or range. We've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years. So long term, we want to try to make about 20 million vehicles a year.
That's a lot.
I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about
Wow.
the $25,000
That's
price
awesome.
point, you have to consider how.
And here's another one that I think is a big deal to me because I would love to see a $25,000 full self-driving electric vehicle on the road.
And we should probably talk about the Model S Plaid. What about that? We're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise.
Wow. That's crazy. Alright, next up they go into some Q&A.
Hey guys, Eli here from Tesla Owners Club, My Tesla Adventure. Just a quick question. So I'm a huge fan of car camping in my Tesla with my dream case, like my all-time favorite activity. Is it going to be possible to get climate control to the back of the Cybertruck? Because that would be the ultimate camping machine if we can get all-night climate control.
We'll try to do that. Yeah, I agree. That would be really cool. Yeah.
How does the ICE industry look like for in the future?
Well, I don't think there will be an ICE industry long term. I mean, well, I guess there might be like a few things that are like, it's a like curious thing. Like, I mean, there's still like some steam engines made somewhere, but like they're just basically sort of quirky collector's items. And I mean, that will be the future of the internal combustion engine car.
I think the thing that people haven't fully internalized is once we do get to the 25K car, the ownership cost of that car is incredibly lower than the prior car. And then on the solar side and wind, with the cost of solar and wind coming down, and with batteries coming down with them, the actual cost of energy on the grid is going down. So we're sort of moving towards a sustainable lower cost future. And really the goal that we were trying to present here was a model for vertical integration, strategic vertical integration that a lot of different people can do. What we need to see is vertical integration that shortens the process path from mine to cathode.
Another side note, this is another one of those things that guys like Henry Ford and Thomas Edison had done quite a long time ago, where Henry Ford, for instance, had created a separate company to make rubber for the tires and also had created a mining company to mine for the metal to make steel.
And I think actually, as we go to a more autonomous future, the importance of entertainment and productivity will become greater and greater.
It just so happens that the way the North American connectors are on all the cars in North America, it doesn't matter whether it's the Tesla connector or the connector that the other vehicles have, doesn't actually support powering your home.
To create a specification, our design team is working right with the manufacturing team to allow us to speed that process up tremendously. So.
Yeah, it's definitely a important part of the vertically integrated approach is to be able to design the factory around the equipment, in fact, together with the equipment, so that you can build the factory at lower cost and more quickly.
Alright, well there you go. if you end up watching the full video, just know that it's a bunch of technical jargon, but what it really boils down to is that Tesla has a clear plan to be able to make cheaper and better batteries. And that's going to mean cheaper and better electric vehicles, and that might even mean cheaper and better tools and other things. Drop me a line in the comments and let me know what you think about this whole thing. Thanks so much for watching the video. See you next time. Alright, there you go. And if you end up watching the full video, just know that it's a bunch of technical jargon.
For a sustainable energy future, the spice must flow. Thank you.
Spice must,
Yeah, indeed.
spice must flow.
The new spice.
Oh, so it's not Old Spice.
I don't know. I think the